Contour integration using Jordan's lemma, assignment 9. Now in some of the examples or in net exams or subjective papers, already function in terms of z will be given to you, right? And you have to prove the integration by integrating that given function which is given to you in terms of z, right? So there is no need to guess the function f of z in that questions. So in this assignment 9, I'm going to solve such kind of examples where already function in terms of z is given to us, right? So let's start. By integrating log of 1 minus iota z over z square minus 2z sine alpha plus 1 around a suitable contour, prove that integration minus infinity to infinity tan inverse x over x square minus 2x sine alpha plus 1 dx is equal to pi alpha over 2 cos alpha. Now if you look at this example, I need to prove this integration and also the function is given to me which is in terms of z. So by making use of this function, by starting our integration from this function, I will prove this result, right? So just same as what we have done in the previous questions. The difference is that where we guess the function in terms of z, here this function is already given to us in the example, right? So we integrate f of z is equal to, now what is f of z given to us? Yes, it is log of 1 minus iota z over z square minus 2z sine of alpha plus 1, right, where alpha is strictly positive. Fine. Okay, along the contour C. So first step is we have to find out the poles, and taking the denominator to be equal to 0, clearly z is equal to, now this is the equation, quadratic equation. So I'm getting the poles z to be equal to sine of alpha plus minus iota cos of alpha. If you solve, you will get this, of which only, yes, which pole lie inside the contour? The positive one, which means sine of alpha plus iota cos of alpha lies inside C, right? So second step is to calculate the residue of fz at the pole which is lying inside the contour. And the formula for that is just write the numerator as it is and derivate the denominator with respect to z at z is equal to sine alpha plus iota cos alpha. So I'm writing log of 1 minus iota z, okay, derivating this, which is 2z minus 2 sine alpha at z is equal to sine alpha plus iota cos alpha. Now putting the values of z over here, so this is log of 1 minus iota, this is sine alpha plus iota cos alpha, and in the denominator this is 2 times sine alpha plus iota cos alpha minus 2 sine of alpha, right? So this 2 sine alpha will cancel out with this, right? So this is equal to log of, okay, if you solve this, this is 1 minus iota sine alpha and iota square is negative 1, so this is plus cos alpha. So I'm writing 1 plus cos alpha first and then minus iota sine alpha, the remaining one. And in the denominator I'm having 2 iota cos alpha. Fine, okay. Now I know that log of something is equal to log of mod of that, right, minus iota argument of this thing which is in the bracket. And please note that argument of z, if z is x plus iota y, then argument of z is tan inverse y over x. So what is the argument for this? So argument will be tan inverse sine of alpha over 1 plus cos alpha with negative sign. So that will be log of mod of this thing. Suppose this is equal to z naught. So the formula will be for the numerator log of z naught is equal to log of mod of z naught plus iota argument of z naught, right? Because argument is tan inverse y by x. So this is, here I am having the negative sign with the imaginary part. So this is negatives of sine alpha over 1 plus cos alpha. So this negative will come outside, and here this will be positive sign will be changed into the negative, right? So I am doing that. So this is equal to log of, okay, what is the mod of 1 plus cos alpha minus iota sine alpha? That is square root of this 1 plus cos alpha whole square plus sine of alpha whole square. So log, if this is square root of 1 plus cos alpha whole square plus sine of square alpha. Okay, shall I write the formula? Is there any need to write the formula again? Is it clear if I solve directly? See, log of mod of z naught. What is mod of z naught? Real part whole square plus imaginary part whole square. Clear to you? Okay, that is I have written. And then is minus iota, the argument, because here I am having negative sign. So this positive sign will be changed into negative 1. So this is iota tan inverse sine of alpha over 1 plus cos alpha. Very fine. Okay. This is a property, right? That negative will come outside. So 2 iota cos of alpha. Okay. So next step is, I'm writing this as it is. 1 plus cos alpha whole square plus, there is no need to solve this, we don't need here iota. Okay, can I write sine of alpha as 2 sine alpha by 2 cos of alpha by 2, this is the identity, and 1 plus cos alpha, I know this is 2 cos square alpha by 2. So if you cancel all this, you will get here tan of alpha by 2. So I'm writing here as simply tan of alpha by 2. Clear? Divide by 2 iota cos alpha. So next, log of square root 1 plus cos alpha whole square plus sine square alpha minus iota, this tan inverse tan that will go, so this is just alpha by 2, and divide by 2 iota cos alpha, right? So now I am going to use the Cauchy residue theorem, the third step. Let's move forward. By Cauchy residue theorem, integral of c f z over c f z dz is equal to 2 pi iota times the residue. And what is our residue? It is log of square root of 1 plus cos alpha whole square plus sine square alpha minus iota alpha by 2 over 2 iota cos alpha. Fine. Now splitting the c in real along the real axis and then along the semicircle tau. So this is equal to 2 iota iota cancel. So here I am having now pi over cos alpha, and then the complete numerator log of 1 plus cos alpha whole square plus sine square alpha minus iota alpha by 2. Very fine. Mark this as 1. Now the last thing is just we have to let r tends to infinity in 1, and using the Jordan's lemma we know that this integration will always comes out to be 0. Just write straight away like this. In the lengthy questions there is no need to prove this to be equal to 0. Just keep the statement as letting r tends to infinity, and using the Jordan's lemma this integration is equal to 0. Right? For such kind of examples there is no need to prove this to be equal to 0. Just write the condition. So we get now letting r tends to infinity in 1, so changing this r to infinity, so I'm having minus infinity to infinity. Alright, now here the function fx will be log of 1 minus iota x. What is given to us? The function which is given to us is in terms of z, but now I have to write this function in terms of x because the integration is along the real axis. So put x in place of z. Very important. So my function fx is log of 1 minus iota x over x square minus 2x sine alpha plus 1 dx is equal to the right hand side. Now again I'm using the formula. What is log of 1 minus iota x? Log of mod of this plus iota argument of 1 minus iota x. So this is log of, okay, what is mod of 1 minus iota x? This is 1 square plus x square square root. 1 plus x square, and then plus iota times argument is again tan inverse y by x. Here y is negative x, so tan inverse negative x, and because it is tan inverse negative x, negative will come outside, so this is minus iota tan inverse x, right, over x square minus 2x sine alpha plus 1 is dx is equal to pi over cos alpha log of square root 1 plus cos alpha whole square plus sine square alpha minus iota alpha by 2. Now because in the example I need tan inverse in the numerator, see, and I have got finally tan inverse x. Alright, tan inverse x in the numerator, so I have to equate real parts or imaginary parts. I have to equate the imaginary parts because tan inverse is with iota, so I have to equate the imaginary parts. So equating the imaginary parts, sorry, this is minus infinity to infinity, I'm very sorry. So this is okay, because I'm going to equate the imaginary part, I'm taking this negative outside the integration. So this is negative of minus infinity to infinity tan inverse x over x square minus 2x sine alpha plus 1 dx. So this is equal to, okay, now here the imaginary part is negative alpha by 2 into pi over cos alpha. So pi divided by cos alpha into negative alpha by 2. This negative will cancel out with this negative, and this is minus infinity to infinity, almost it's done. So this is x square minus 2x sine alpha plus 1 dx is equal to, finally I get the result, pi alpha over 2 cos alpha, hence proved. Right? Just 4 steps. Calculate the poles. Find out the residue at the pole which lie inside the contour. Then use the Cauchy residue theorem. And then at last, letting r tends to infinity. Right? And using the Jordan's lemma. You will easily get the result, and you have to check which part you have to equate by looking back into your example, the given example. Alright, this is an exercise for you. Prove that integration minus infinity to infinity sin x over x square plus x plus 1 whole square dx is equal to 2 pi square root 3 plus 2 over 3 root 3 into e raised to the power negative root 3 by 2 sine of 1 by 2. Please don't worry, the function is given to you in terms of z. So you have to integrate f of z equal to e the power iota z over z square plus z plus 1 whole square along the c, where c is your contour. Please use this function. Start from this function, integrate this function. You will definitely get this result. It's very easy, 4-step solution, right? Just try this example. Alright, thank you. God bless you all. This is the last assignment for the contour integration using the Jordan's lemmas. In the next video, I'm going to start the case of poles on the real axis. So we will start with the examples where the poles will lie on the real axis, right? Till now we have done the poles lying inside the contour. But now in the next session we will do the case of poles which lie on the real axis, right? Alright, thank you. Have a nice day.